This is part 4 of the Module 4 lecture. Now that we reviewed the structure of a marginal contingency table and how it's arranged and all these properties, now let's look at the calculation of probabilities where we rely on a contingency table. So the first one is what is called the marginal probability. So the marginal probability is the probability of a single event without regard to any other related event. In this case, let's look at an example to illustrate this. So the example is asking us to, what is the probability that a worker in the US selected at random is stressed? And in here, we're going to designate B as the event the worker is stressed at work. So if you look at the contingency table, all these workers, these 282 females and these 244 males, are stressed. So the total number of stressed workers out of these 1,501 workers that were interviewed are stressed. So we want that marginal probability of being stressed without regard of being a male or a female. So to calculate that probability, we just divide 526 by 1,501. We get 0.3504. So we can interpret this number as the probability that a randomly selected US worker is stressed, regardless of its gender, is 0.3504 or 35.04%. Now notice that this is one of the marginal probabilities that you can calculate. You could have calculated the probability of the worker not be stressed, which would be 975 by 1,501. Or you could have been asked to calculate the marginal probability of the worker being a female. Then you will divide 762 by 1,501. Or you could have been asked to calculate the marginal probability of a male. In that case, you will take 739 and divide it by 1,501. So you see that in this table, you have 4 possible marginal probabilities. So keep in mind, because when you're given a problem like this, you could be asked any of these marginal probabilities. All right, the next interesting probability calculation is the joint probability. So the joint probability of events A and B that we're going to designate as the probability of A and B is the probability that A and B occur simultaneously, or in other words, we say that this is the probability of the two events intersecting. Let's look at an example to see how this works. What is the probability that a worker in the US selected at random is a male? Let's call that event A. And that he is stressed. Let's call that event B. So if we look at stress worker, and then being a male. So here's the category of stress workers, and here's the category of male workers. So this 244 marks the intersection of male workers with stress workers, or the joint probability of these two classes. So to calculate this probability, then we divide 244 by 1,501. If you do that, that results in 0.1626. So we say, we interpret this number as the probability that male worker in the US selected at random is stressed is 0.1626 or 16.26%. Now, there are 4 possible joint probabilities. That of the female and stress, female and not stress, male and stress, the one we just calculated, and male and not stress. So again, if you are presented with this table, you could be asked to calculate any of these 4 joint probabilities. All right, so we looked at marginal probabilities and joint probabilities. I don't think this surprises you given how we explain the components of a contingency table or a two-way classification table. All right, another very important concept of calculating probabilities is the conditional probability. So conditional probability is a probability that is updated once you know something about a related event. To give you an example, you may remember at the beginning of this problem with COVID-19 that people kept on talking about the mortality rate. That is the probability of dying once you get COVID-19. If you recall that in the US in particular, at some point people start asking, well, we noticed that more African Americans and more Hispanics are dying than white Americans. So when you condition on the ethnicity or the race, then the probability of dying due to COVID-19 changes. So if you are African American, you have a higher chance of dying than if you're a Hispanic or a white American. If you're a Hispanic, you have a higher probability of dying than a white American. So conditioning is a very important aspect, because that's when you take an overall probability and then you condition on a particular event and you update that probability given that event. So the conditional probability of A given B, we designated this as probability of A vertical line. The vertical line means given that the event B is observed, or we want to find something about A given that we know B. And this is defined as the probability of A given B is the joint probability of A and B dividing that by the probability you are conditioning on. So here you're looking at the elements common to A and B, and you divide that probability by the probability of B, the one you're conditioning on. Now you can reverse the conditioning. So now let's say that you want the probability of B given A. Well, again, in the numerator you have the joint probability of A and B, and you divide it by the probability of A, which is the one you're conditioning on. All right, let's see how this works in a contingency table. So again, we're looking at the same contingency table as before, where we have the 1,501 workers in the US that were asked if they were stressed or not, and their gender record. So the question here is, what is the probability that a US worker is stressed given that the worker is a female? So given that a worker is a female, that means we're conditioning on the worker being a female. That conditioning on the worker being a female, that means we focus only on female workers. So we ignore everything else because we are only interested in the female workers. We're saying, given that it's a female, what is the probability that a worker will be stressed? Well, focusing only on the female row, then you see there's 282 female workers that are stressed out of the 762 females in this population. So the conditional probability of stress given that it's a female is just 282 divided by 762, which is what I have right here. Now, if you decide to look at the formula and say, well, I'm going to apply the formula, well, the probability of A and B are the common elements to the being stressed and being a female, and that's 282. To calculate that probability, you divide by 1,501. So that's the joint probability of A and B. And it says, well, I'm conditioning on females, which is the event A. So the probability of A is the number of females divided by 1,501. That will be the relative frequency, which corresponds to the marginal probability of a female. Now, you see that this 1,501 in the numerator cancels with that number in the denominator. So you end up with this figure. So if you proceed this way, calculating probabilities, or you simply ignore everything else and take the event of interest and divide it by the marginal probability, because we're conditioning on that row of the contingency table, then you can just simply divide 282 by 762. All right, so this 0.37 is interpreted then as the probability that the U.S. worker selected at random is stressed given that the worker is a female is 0.37 or 37%. Again, you may be asked questions where you condition on the worker being a male, or you condition on the worker being stressed, or you condition on the worker not being stressed. So there are multiple conditional probabilities that could be that you could be asked to calculate, depending on what you're conditioning on. All right, I hope this is clear in your mind, because this is a likely problem that you are going to find in your homework and in the exam as well. All right, good. So let's look at other situations where conditional probability arises. So here's an example where a card is drawn from a standard deck of cards, and the remaining cards are shuffled, and a second card is drawn. So the question is, what is the probability that a second card is an ace given that the first card drawn was an ace and was not returned to the deck? If you don't play cards, but if you do, then you know that there are 52 cards in the deck, and 4 cards are aces. And I'm talking about a standard deck of cards. All right, so the probability of getting an ace in the first draw is 4 out of 52. There are 4 aces in the deck, and there are 52 cards, and you're drawing at random, and every card has an equal chance of being selected. Now, so you draw the ace, you grab it on your hand, and you say, okay, now with this ace in my hand, what is the probability that I will get another ace in the second card? Well, now you have only 51 cards left and 3 aces left, because you have 1 in your hand, and so you have diminished the number of cards in the deck by 1. So the probability, the conditional probability of getting a second ace, given that you already drew an ace, is of course 3 divided by 51. So this is another example where the marginal probability can come to help you answer a question. Here's another example. In this case, again, we're not using a contingency table, nor we're using a situation where we can use a theoretical probability, but instead we're going to use the relative frequency probability. So the probability that the senior graduating from a private university has a student loan to pay after graduation is 0.6. The probability that a senior graduating from a private university is a male and has a student loan to pay after graduation is 0.24. The question is, what is the probability of randomly selecting a male senior student graduating from a private university given that he has a student loan to pay? So if you look at this, there are 2 events involved, that of being a male and that of having a loan to pay. So this 0.6 is the probability that a senior graduating from a private university has a loan to pay is 0.6. And the probability that the senior is graduating from a private university is a male and has a student loan to pay is 0.24. So here I'm reflecting the 2 events of interest and the probabilities that I'm given. Now the question is, what is the probability that the senior is graduating from a private university is a male and he has, given that he has a loan to pay? So the joint probability is 0.24, and the marginal, or rather the probability of him having a student loan to pay is 0.6. If you carry out this calculation, you get 0.4. So the probability of randomly selecting a senior student graduating from a private university with a student loan to pay is a male is 0.4 or 40%. All right, so with this I show you 3 examples of how the conditional probability could come into a problem and how you can address this. All right, in the next segment, now we're going to talk about independent events.